One of the quality dimensions that belongs to the conformance level is the precision. Precision is basically the idea of, so precision measures try to establish the relationship between the observed behavior, so the behavior in the log, and the possible behavior, so the behavior that is in the model. In other terms, with the precision measures, we want to capture how much of the behavior that is in the log, in the model, is actually observed in the log. And the dual, let's say, the dual projection of this concept is how much behavior of the model is not observed in the log. And this might be useful to quantify also the generalization. So there are several measures for computing the precision. Let's start by talking about the simple behavioral appropriateness. Here the idea of this measure is to compute the average number of transitions that are enabled during the replay of a trace. So basically the idea is to replay the trace and to compute how many transitions were enabled at each event that is replayed. And here, the more transitions that are enabled, the more decision points that the model provided, and the more parallelism that was in there. Therefore, the more decision points and the more parallelism suggests the presence of additional behavior that the model supports, but that was not observed in the log. The idea is then to normalize this quantity, so the quantity of number of enabled transitions during replay, over the total number of transitions of a model. And then this is the definition of the simple behavioral appropriateness, which is basically given by the number of the total number of transitions in the model minus the number of enabled transitions, and all of that is then normalized over the total number of transitions in the model, and these quantities are actually multiplied by the number of occurrences of each trace in the log, summed up for all the traces, both at the numerator and denominator. So the idea is that this measure returns a value between 0 and 1, where 0 means that basically all transitions were always enabled, so a pretty low precision. Instead, the value is 1 when the precision is maximum, meaning that the just one transition was basically enabled, so the path was very much defined. So let's see a couple of instances. If we have the flower model, then the point here is that all transitions are always enabled during the replay of any trace. So the simple behavioral appropriateness measure will point towards 0. Maybe it will not be 0, but it's very close to 0. Instead, if we consider the sequence process model, then we have that during the replay of such a model, we have always at most or exactly one transition enabled, which means that during every replay we just have exactly one transition, and so the behavioral appropriateness would be 1, so the maximal one. So the problem of that measure is that because of this definition, you can get a value of 1 only for sequential model. So this measure is actually appropriate just to compare models, but is not really that useful in absolute terms. In addition to that, this measure assumes that it is possible to replay the log on top of the model. So somehow it assumes a perfect fitness between the log and the model itself. A more advanced metric is called advanced behavioral appropriateness. And here the idea is not to focus very much on the replay, but to generalize a bit and to investigate how much behavior of the model is required in order to explain the traces in the log. So the idea is to calculate two ordering relations, following and predecessions. And these are actually not directly following or directly precedes relationship, but they are indirect. So for example, X follows Y means that there is a trace where Y happens before X, and with the precedes it's the other way around. These two relations can happen for all activities in three variations or three frequencies, if you will. So always, which means that a certain relationship holds in all the traces. Sometimes, meaning that the relationship holds just in some of the traces, and never, meaning that the relationship never holds. And then the idea of this behavioral appropriateness is to compute these two set of relations for both the model and the log. And then the idea is to compare them. So let's see an example here. Here we have this process model, and we can compute the follows relation for that. And for example, we might see that D always follows B. And this is one example of relation that also is characterized as always. And here you can see the whole matrix for this, the whole relation follows for this model, where the specific quantification is also reported as always, never, or sometimes. Then, given a log, we can compute the same relationship for so the same relationship follows and precedes for the log as well, which is obtaining here. And then the idea is to basically compare the two the four matrices. So the two matrices for the follows and the two matrices for the precedes. And then the quantification of the advanced behavioral appropriateness is defined as depicted in the formula up here, where we basically have to compare the intersection of the behavior. So how much of the behavior is shared between the two matrices by computing the cardinality of the intersection of, in this case, it's the follow relationships between the follow relationship of the model and the follow relationship of the log, and how big is the intersection. And this is then normalized over the size of the relationship for the model, which is twice the size of this. So the advanced behavioral appropriateness is the quantification of this plus the same quantification, but this time computed for the precedes relationship instead. And in this way we have a way of quantifying how much of the behavior is needed in order to explain the log.